Hi, I'm Mandy Limiak, and I want to tell you a little bit about the Department of Agricultural and Biological Engineering today, specifically Environmental and Natural Resource Engineering, or ENRE. So when most people are out in nature, they see wetlands, they see drainage ditches, and they just see that there are plants and water there. They don't really consider how the design of those spaces actively help our environment. And that's where ENRE comes in. We design engineering projects, ecosystems that use natural resources like soil, water, plants, and that helps reduce ecosystem pollution in ways to help us all. Without systems like this, without these engineering designs, we can face these global threats of algae blooms, erosion, climate change. So I want to introduce you a little bit to the idea of environmental engineering and some of the concepts that we work with today in a more hands-on fashion. So the first activity we're going to do today is hands-on. You can do it at home, and it's teaching you a little bit about the design process and how engineers design things to help the environment. So our problem is that there was a spill of a toxic chemical, and it's very close to this creek that you see on our map. So this is a watershed map. It shows you that any water within that area will eventually drain to this out point, which says it goes to a reservoir. This reservoir is providing drinking water to people in a nearby town, and so we need to make sure that this toxic chemical spill does not reach the reservoir. Your job as environmental engineers is to determine a few different things. We're going to figure out the best place to sample and to add our filter, and then the best kind of filter you can build within your reasonable budget. And luckily, when doing this lab, it's mostly done with all things you have at home. So the first part we need to do is figure out how far the contamination has already traveled. Typically, when contamination is entered into a stream through like storm drains, as this one would have been since it was spilled near the river, not directly into it, we know it's traveling downstream. We know that it is diluting as it goes. If you're not familiar with dilution, that's where you add more and more water to something, and therefore its concentration gets less and less. The way we're going to check to see our progress is by testing for turbidity at all 4 of those sites, the spill site and then 1, 2, and 3, to determine where the best place will be for our new filter. Turbidity is a measurement of cloudiness, and so it just tells you how much stuff is suspended in the water. This chemical does form a bit of a suspension, and so we can then filter it out, but we need to know how much and how far it's gotten. But it also dissolves some. So it can combine with soil and be suspended, but it also can dissolve within the water. And when it does, it actually acts the same way as glucose does with an enzyme. So we're able to test for both options this way. And that will help us later determine which filter is the best option. So in order to test for the turbidity, what we do is we collected the 4 samples you saw on the map, and we're going to check them while we're in the field. This is called a turbidimeter. It's field size, fits right in your hand, so it doesn't require a lot of equipment. You can throw it in a truck and bring it with you. It's great for on-the-go measurements. And we're going to check the turbidity of our samples. I'm going to show you what they look like. So our samples look like this, and you can tell, even just by looking, that there's a very clear gradient of contamination here. So this one is our spill site. Very muddy. Looks like it's definitely been contaminated. This is site 1. So this is that spot right nearest the spill site where it enters the river. And you can tell some of it has definitely made it into the river here. With site 2, it's a little harder to tell because sometimes rivers, especially during high storm events, can look kind of cloudy like this anyways. So what we're going to do is compare it to site 3. Now you can see site 2 definitely has more in it. And so if this is what the stream normally looks like, then there's definitely been some contamination that's made it to site 2. but site 3 is clear. So when we look at these, we're going to say, even just visually looking without taking our turbidity measurement yet, we can say that site 2 is probably the best place to locate our filter if we want to get as much contamination out of the river as possible. We don't want to put it in up here at site 1, or we'll have missed everything that already made it past site 1. So in order to check our turbidity, all we have to do, this works in a really simple way. It's got a light beam in it. There's a light bulb down here. And we're going to put our sample in this hole right here. It's going to shine a light right through our sample, and the sensor on the other side is going to tell us how much of that light came through and how much of it got deflected by all of the sediment that's floating in our soil. So we're going to check site 2, since we know that's where we want to place our filter. This is going to tell us what our starting point is for our filter then. Fill it up. Comes with these nice little vials. They're not too hard to use, which makes this a great field toolkit. And since it's light and your fingerprint on glass can reflect light, we don't want to reflect anything accidentally. So we're going to wipe any fingerprints off. Put it in our turbidimeter. Cap it up so no extra light can come in from anywhere else. And then we're just going to press measure. It's going to give us a number. Okay? Then we're going to check for glucose. So we're going to use these little test tubes. They're called centrifuge tubes. They're just plastic and convenient in this case. And we're going to take some of our sample with a little pipette here. And then we're going to add some of this enzyme that reacts with glucose. So when this enzyme reacts with glucose in water, it turns a pink color. So the more glucose you have in your water, the more pink it will be. We add that in. Cap it up and give it a good shake to make sure it's well mixed. And then we just wait, and the pink color will start to form. So once we've been able to determine where our filter goes in site 2, we know what kind of levels we're starting with for our glucose and our sediment trapped contamination. So that will give us our best option for where moving forward and what our filter needs to do. So once we figure out the best place, we're going to, in this case, you're not going to get to compete against other groups, unfortunately. But if you've got other people in your house, you can definitely set up a competition and see who builds the best filter system for a budget. So the goal is to get the lowest turbidity, the least cloudiness, and typically we would also look for the lowest glucose, but unfortunately you won't have this enzyme at your house like I have here and would have here if you were able to be here in person with us. So what we're going to do is I'm going to show you the list of typical materials we would build with. And most of them are things you probably have around your house. If you are missing some, if you don't have them, or maybe you think of another idea, go ahead and give it a try. So the best thing is, all you really need is a 2-liter bottle and a cup and some dirty water. So go ahead and fill up a cup of water, add a little bit of soil from your yard to it, make yourself a little bit, not too muddy. We don't want mud, we just want dirty water. It'll look like my examples I showed you. And then anything like this, if you've got coffee filters or cheesecloths or cotton balls, sand from the sandbox, gravel, maybe you have a gravel driveway even. And then we use things like rubber bands sometimes as structural support. Go ahead and look around your house and see what kind of options you have and see what kind of filter you think you can build. Then all you have to do is build your filter, pour the muddy water in the top, see how clean it is when it comes out the bottom. If you have clear glasses or cups of some kind, those are the best ones for seeing your results. And if you're lucky enough to be competing against your family members in your house, then compare your results and see whose looks clearest at the end of the day. Who do you think has the least amount of turbidity? And then, since you've got some time, go ahead and try varying it up a little bit. Make some changes. What do you think would work better? Is your budget a problem? All of these things are real world problems that engineers have to design around. They have budgets they have to work with. They have only certain equipment and things they can use sometimes. Also, is your filter sustainable? Are we going to be able to run millions and millions of gallons of contaminated water through it and not get clogged up? Or do you think it'll clog and have to be replaced frequently? Those are some things to think about. All right, now to build your filter, all you need is a 2-liter bottle. Cut the bottom of it off. We cover ours in tape to make sure that you don't have any sharp edges. And a cup. That's the only major requirement here. And really, you could probably use something that's similar to this, but plastic is good since it won't leak through like it would cardboard or seep into wood or something like that. So you've got the budget, you can see it up on the screen, and we've sort of generalized what these household items represent in environmental engineering. So a medium-sized membrane filter is like a coffee filter. You use coffee filters because it holds the grounds but lets through the water. If you don't have some of these things in your house, I'm sure you don't have activated carbon. I'll show you what that looks like though. That will help us remove the glucose, which unfortunately you can't test for at home anyways. So we're going to do ours based off of turbidity anyways. What I want you to do is find a few things around your house that match these sort of ideas. A large pore membrane filter. We have cheesecloth. Something else you could use would maybe be even like some paper towel. A loosely woven fabric piece. We've got cotton balls. A lot of people have those in their house. If you don't, maybe that's where a wad of tissues would come in. That sort of thing. We can be flexible here. But try to find something representative and then stick with the budget. Part of the engineering design challenge is that you have to do it within a budget. So what we're going to do, and I'll show you a little bit of an example, but I won't give you all my secrets, is build a filter and then we're going to test it out. And so this is what's great that you can do at home. You can do it in competition with your friends and your family. See whose looks the clearest when you put it into a clear glass at the end. Just like you could see the levels of cloudiness in our samples earlier. You can even compete against yourself and try multiple different types, arrange them different ways, use different pieces of materials, see which one works best. Remember, we're also going for sustainability here. We want them to work for a long time. So I'm going to start with structural supports. So you get 2 rubber bands for $5. Easy enough. And then I'm going to get a coffee filter because I think at the bottom of mine, I want to put a coffee filter in order to help hold it all in because this hole is a little bit big. So use a rubber band to tie it on. Okay, now I think I'm gonna put a few cotton balls in the bottom. So the quantity is 2 for $15. That puts me up to 20. Oh, my mistake. You can have 5 for $15. So we'll put all 5 in there. Just for a little extra support here. And if you've got younger kids in your house, you can also use this as an opportunity to help work on your math skills. How many of each item are you ordering? You got to multiply by the cost, add it all up for a total cost in the end. Now that I've got my cotton balls in here, I think I'm going to throw in some activated carbon. So this is what activated carbon looks like. And if you've ever seen something like a Brita pitcher filter, it comes in that cartridge, or your refrigerator filter. They often have and are made with active carbon. So the way this works is this carbon has been burnt down. And when that happens, it creates a lot of really rough, uneven, jagged craters in the pieces of carbon. So those little pieces, those little areas, nooks and crannies basically, can collect things. Things will stick to them and adhere in them, like our glucose. If we can if we throw glucose through here, then the carbon will hold on to that glucose and let the water keep passing through. So we're going to use that in this case for a little bit of glucose monitoring. We want to get rid of as much of the contaminant as we can, because remember, this is people's drinking water we're talking about. And then I think, because let's see, activated carbon is $15, so now I'm up to $35. I'm going to add some sand. Sand, if you think about it, can make a great natural filter, because what's in the ground? How does groundwater get clean enough for us to drink out of our wells? It has to pass through layers of soil and sand and rock and clay. Sand is very small pieces, so it takes a lot for the water to pass through all those tiny little pieces. Now I suggest you go around your house and see what you've got that you can use to build your filter and get started. Once you've got it built up, take your sample. Remember, we made it look a little bit like Site 2. Open it up, set your filter over its cup so that you can collect the water at the end, and pour it in. Okay? Let us know how you did.